First media is having refractive index 3 by 2, second media is having refractive index 4 by 3. When refraction will take place from 1 to 2, then we have sin I upon sin R as mu 2 upon mu 1. Always जहां से हम जहां पर जा रहे हैं तो this will be at the top. So sin 30, because angle of incidence is given to be 30 degree. Sin R हमें calculate करना है in this manner. If you will calculate, your sin R is coming out to be 0.5625. अब दूसरा देखते हैं medium 2 to medium 1. So now when you will be entering from 2 to 1, sin I upon sin R becomes mu 1 upon mu 2. Of course, क्योंकि इस बार हम 2 से 1 में जा रहे हैं, so 1 upon 2. 3 by 2 upon 4 by 3 and there sin R 0.4445. So this is how you can calculate that you will be moving from denser to rarer or you are moving from rarer to denser. Accordingly the value of angle will change. If it is from denser to rarer, then the bend will move away from normal, and then when you will be moving from rarer to denser, it will bend towards normal. On this background you can have the concept of medium 1 to medium 2 and medium 2 to medium 1. Very, very important numerical problem. Be careful when you will deal with the concept of ray optics. The first video has already uploaded. This will be the second video of ray optics. So you can now go through first problem of today, that when refraction will take place from medium 1 to medium 2 or from medium 2 to medium 1. Second concept is for the real depth and apparent depth. We know the formula. Refractive index is always equals to real depth upon apparent depth. In the given problem, if it is given that refractive index is 1.3 and apparent depth is found to be 7.7, what will be real depth? In this sense, real depth can be calculated as mu into apparent depth. The value of mu is given 1.3, apparent depth is given as 7.7. If you will multiply 1.3 to 7.7, your answer is 10.01. If this is in centimeter, this will also be in centimeter. This is your problem number 2 in terms of real depth and apparent depth. Sorry. Next. In the third part, very, very important question again. You have a glass and there you have a scratch at the bottom of the glass. In this glass, 3 different layers are there of the liquid. This will be with 1.5, this will be with 1.3, this will be with 1.2. Each is having 10 centimeter of depth. We want to find out कि ये वाला जो स्क्रैच जो इसके लास्ट पे लगा हुआ था ये कितना ऊपर की तरफ उठ जाएगा. We will have to go with apparent shift. T1 1 minus 1 upon mu 1, T2 1 minus 1 upon mu 2, T3 1 minus 1 upon mu 3. सारे T10 है. 1.5. सिंप्लीफाई करें तो 10, 10 और 10, 30 तो एक साथ आ गए, माइनस 10 अपॉन 1.5, 10 अपॉन 1.3, 10 अपॉन 1.2. जो एक्चुअल डेप्थ आपकी 30 थी, नाउ इट विल रिड्यूस टू दिस मच. You will have to subtract from it 30 and you will find out the answer like this. Apparent shift of object if you have three different liquids. ये जनरल फॉर्मूला है, कितना शिफ्ट होगा उस शिफ्ट के लिए हमें इस तरह से कैलकुलेट करना पड़ता है. कंसेप्ट नंबर 4 नाउ. वेवलेंथ एयर में दे रखी है हमें 6000 एंगस्ट्रम. जब ये लाइट किसी रिफ्रैक्टिव इंडेक्स 1.5 में एंटर करती है, what will be the new wavelength? So हमेशा याद रखें that wavelength in medium must be equals to wavelength into air upon refractive index. 6000 upon 1.5, it's coming out to be 4000 angstrom. Velocity in air, question number 5. Is given as 3 into 10 raised to power 8. Velocity in medium is given as 2 into 10 raised to power 8. On the plane surface, you have one ink dot here. When this medium of 6 centimeter thickness is placed, then how much it will shift? Find apparent shift. First of all, you need to find out what is the refractive index. Refractive index is V air upon V medium. So this is 3 into 10 raised to power 8 upon 2 into 10 raised to power 8. It is 1.5. We know the formula of apparent shift. Apparent shift is actual thickness 1 minus mu. Actual thickness 6, 1 minus 1.5, it's coming out to be 2 centimeter. So it will shift to 2 centimeter from the bottom. This is again glass. Here you have a scratch on it. Ten centimeter of liquid of refractive index 2 filled in this. Same glass, same scratch, 10 centimeter, but this time this must be of 1.5 refractive index filled to this. Compare apparent shift in position. यहां जब मुझे apparent shift देखना है, I'll go like this. T. तो सबसे पहले यहां पर देखते हैं apparent shift 1, it should be 10, 1 minus 1 upon 2. Apparent shift 2 is 10, 1 minus 1.5. This result is 10 upon 2, so it should be 5. This result is 10, 1.5 means you can say it should be 2 by 3. So it should be 1 by 3. And then if you will compare AS1 so it should be 3 by 2. So especially these questions which are of apparent shift that you can calculate or you can explain it in this manner. Very, very important concept, but the formula remains same. T1 minus 1 upon mu, and mu equals to real depth upon apparent depth, where mu is having different concepts. Next concept is total internal reflection. Basic logic that if light will come here at the critical angle, then angle of refraction becomes 90 degree. And if it is more than the critical angle, light will reflect back. So two conditions for TIR. Number one, light must pass from denser to rarer. Second, angle of incidence must be more than critical angle. We know mu equals to sine I upon sine R for rarer to denser. But because in TIR, it always from denser to rarer, so it should be equals to sine R upon sine I. Sine 90 upon sine IC. You have the relation mu equals to 1 upon sine IC. This is relation between refractive index and critical angle. it shows that mu is inversely proportional to critical angle. More refractive index, less critical angle. For water, air interface, critical angle is found to be 48.75. For refractive index of 1.33. For glass air, for 41.14 degree, refractive index, as we know, around 1.5. For diamond, refractive index is very high, 2.42. So critical angle is around 24. You can clearly see more will be refractive index, less will be critical angle. Maximum will be there, refractive index will be there for diamond, so minimum critical angle will be there for diamond. And that's why total internal reflection is very easy for diamond. That is why diamond is sparkle. When light enters through diamond, it suffers total internal reflection and it will come out from a few places only, and that's why diamond appears to sparkle. So it will come out only from a very few places, otherwise the complete light will be collected inside only and repeated total internal reflection will take place. That's why we have, the sparkling of diamond. So sparkling of diamond is an example of total internal reflection. This result is very important. When you have critical angle, you can calculate refractive index. This is how it works. This phenomena is used to construct total reflecting prism. They are also right angle prism. When prism is right angle, when light enters through it, this angle is more than critical angle, because what it needs is 41.4, but this is 45 degree, and it suffers total internal reflection. So we have the 90 degree change in the path. Or you can say 90 degree reflection is there. We can also use the total reflecting prism to invert images also. Two ways are there. Let's see the first one. This is again the right angle prism. Ray of light starting from this point you can clearly see 180 degree change is there. this ray will come here, where this ray will come here. So it's a 90 degree, 180 degree change is there. We can also have without deviation also. See this one. Light will start from this phase, suffer total internal reflection here on this surface. This person who is here will become reverse. So again 180 degree is there. Here you have the deviation, here without deviation. Without deviation in path, and this must be with deviation. So with the deviation in path, 180 degree change in phase. Without deviation in path, 180 degree change in phase is there. Two different cases are there for total internal reflection. The best part is that no multiple images will form, and that's why we generally use total reflecting prism, that there is no multiple reflections, number one. And number two is, the 100% intensity of light will be there. Whatever is the intensity of light here, exactly same intensity of light will be here. So that's why we generally use the total internal reflection, so that we have the conservation of energy and the 100% intensity of light is conserved in this reason we have the total internal reflection things. There are so many other examples of total internal reflection as well. Another important thing is your optical fiber. See the optical fiber. If you will visualize optical fiber, it looks like this. It consists of core and then cladding. This part is called cladding. Core is denser. Comparatively, cladding is rarer. So this is the cross-section view of optical fiber. Now, if you will see the optical fiber cable, this will be denser part, light will enter, suffer total internal reflection, then it will go, and then it will come out. So light, the optical signals can be easily propagated through this way, okay, without any loss of energy. Optical fiber communication is considered to be one of the best communication signals. और किसी एक छोटे से स्पेस के अंदर अगर मैं बहुत सारे ऑप्टिकल फाइबर्स एक साथ लगा दूं, फिर बहुत सारे सिग्नल्स को साथ में भेजूं, then this is called light pipe. Light pipe consists of so many optical fibers in a very narrow space, so that maximum number of signals can be communicated at the same manner without any loss of energy.